Hi, I'm a tutor in Uplatz. Today we're going to discuss about most application framework. The most specification defines not only the lower layers of a most network, which provide the basics for the transmission of data for the network management, but also the protocols and mechanisms for implementing applications on the top of those. In the most specifications, the interface of an application is called the function block and can be compared to a profile of Bluetooth standard. The most application framework permits the creation of applications that are independent of specific implementation on a certain device and of those of the other applications with which they interact in a MOS system. When using the standardized blocks of the MOS specification, reusable and interoperable applications can be developed. An application, for example, that implements the human-machine interface, HMI, for a radio can thus be used with any device which offers the standardized application interface of a radio tuner. Devices of different manufacturers can also be used together if they implement compatible interfaces. This chapter describes the more aspects of the MOS specification that defines the MOS application framework, starting with the description of the device model it is based on. The protocol that application is used to exchange data in a MOS system is described next. Finally, the interfaces necessary for the administrative tasks in a MOS system, as well as the interfaces for typical applications in vehicle infotainment systems and examples for their usage are given. Device model, figure 4.1 shows the model of a MOS device as defined in MOS specification. On the hardware level, a device adds access to the physical transmission layer via the MOS network interface controller. The network service implements a driver layer that controls the access to the interface controller chip and enables applications to carry out basic functions such as sending and receiving messages. In the MOS specification, the interface of an application which offers a specific functionality that is in the context of a group-related functions is referred to as an Fblock. Each device must implement the Fblock net block, which is required for administrative tasks within the MOS system. And the Fblock enhances testability due to compliance reasons. Additionally, each device can, according to its type, implement one or more Fblocks for the functionalities of corresponding applications. For example, it is quite possible that a device offers the functionality of an amplifier as well as that of a radio tuner, which are then each represented by a corresponding Fblock in the system. Most of a model of a MOS device consists of a physical layer with input and output, MOS network interface controller, network services, function block, net block, function block application 1, function block application 2. And Fblock is addressed within the MOS system through its function address. This ensures that its functionality can be accessed irrespective of the physical location of its function. That is, it is not important on which device the function represented by the Fblock are implemented. And Fblock whose function are used and controlled by an application is referred to as a slave. An instance such as an application which uses the Fblock is referred to as its controller. Is shown in figure. Most device, a controller application, slave, Fblock, properties, methods, functions, setting and reading properties, notification of changes, call of methods. Within an Fblock, a differentiation is made between two types of functions. One type is a property that describes a specific attribute of the Fblock that is currently tuned to frequency of a radio tuner. The other, a method that triggers a certain action, example, a scan for the available radio stations. A controller can read the values of the properties of a slave, and if the respective properties support this, modify them. Additionally, the MOS specification defines a notification mechanism by which the controller registers its interest in particular properties of the slave and is subsequently informed by the slave about any changes. Methods are called by the controller to trigger a corresponding action of the slave. After performing the method, the slave returns the result of the execution to the controller. Application protocol. As a central aspect of the MOS application framework, the MOS specification defines a communication protocol for the interaction between the applications in a MOS system. This application protocol is based and depends on the protocols of the underlying channel. In the early MOS system, it was typically used with the MOS control channel. Because of the increase in size of the transmitted content, Currently, the packet data channel is also used more frequently. On the control channel, the protocol for sending application messages is called Application Message Service AMS. On the packet data channel, application messages can be sent using the MOSI protocol MHP. These protocols, which handle, for example, segmentation and flow control, are described in detail in Chapter 5. The MOS application protocol determines how to access the services offered by an application in the MOS system. It describes the data format for messages which are exchanged for that purpose. It further describes the operational sequence and conditions for read and write access to properties and methods of an Fblock, as well as the use of the notification mechanism. A data format, this chapter illustrates the data format of the application message service AMS protocol. It consists of the following elements: device D, Fblock ID, INST ID, FKT ID, opt type data. When describing communication sequence or examples, the above notation is used in which the individual elements are separated by a dot. Basically, the data format contains the following three areas. The addressing area consists of an optional device address, device ID, the identifier of the Fblock ID, and its instant ID, INST ID in the MOS system. The address function with which each function identifier FKT ID, as well as the operation to be applied to the function or type. A data field consists of a length indication length and the data area for the parameters of the function data. The following table shows an overview of the individual elements and their respective size. The elements of the MOS application protocol: element size and description, device ID 16-bit target device address, Fblock ID 8 bits, Fblock identifier, instance ID 8 bits, instance of the Fblock, function identifier 12 bits, function identifier, operation type 4 bits, operation length 16 bits, length of data field, data 0 to 65535 bytes data field. Device address, device ID. The device address, device ID has a size of 16 bits and describes, depending on the context, receiver, and a group of receivers or the sender of a message. When addressing individual devices on the application level, the logical device address is used. Addressing with the node position address is used only for network management or debugging. By using a group address, several devices of a MOS system can be addressed simultaneously. The broadcast addresses 0x03C8 blocking and 0x03F unblocking are used to address all devices in the MOS system. The device address and the different modes of addressing will be described in detail in Chapter 5 MOS protocols. The device ID is not used in higher layers of the MOS network service layer 2, since Fblocks are only addressed via their functional address. The length is not transmitted directly, but is based on the underlying protocol. When programming on an application level, the device address is often not used. Addressing can take place here using only the function address, Fblock, and instance ID. If an application does not know the network address and its communication partner, which is usually the case, it can insert the wildcard 0xFFFF for reference into a message to be sent and pass the message on to the network service. The network service determines the address of the communication partner and replaces the wildcard with it before sending the message. Fblock identifier, Fblock ID. The Fblock ID describes the type of the Fblock and has a size of 8 bits. The Fblock IDs below 0xA0 are defined by the MOS specification with the specific Fblock ID reserved for Fblocks required for administrative tasks, which are called the system Fblocks, are characterizing the specific device function or device type. See table 4.2, section 4.3 and 4.4 of this chapter deal with the system Fblocks and application Fblocks standards with the MOS cooperation. In other areas, the system integrated Fblocks ID from 0xA0 to 0xEF without 0xC8, or the manufacturer of the device Fblock IDs from 0xF0 to 0xFE without 0xFC can define proprietary Fblocks. The Fblock ID 0xFF is used as a wildcard in order to address all Fblocks in a device except for the net block. Structure of the Fblock area, ID area, Fblock name or area, Fblock IDs, description, reserved 0x00 reserved for use by the network service, net block 0x01 system Fblock implemented by each device. Network master 0x02 system Fblock for network master implemented by one device in the system. Connection master 0x03 system Fblock for connection master optionally implemented by one device in the system. Power master 0x04 indicates a power master in the system. Enhanced testability 0x0f implemented by each device. Reserve 0x70 to 0x9f reserved for the future use. System specific 0x A0 to 0x EF assigned by the system integrator. 0xC8 is reserved. Supplier specific 0f0 to 0fb assigned by the device manufacturer. Reserve 0xfc. Supplier specific 0xfp 0xfe assigned by the device manufacturer. Wildcard all 0xff block broadcast. Instance of Fblocks INSTD ID. Since several Fblocks of a certain type may be used in most systems, such as an integrated CD drive, in addition to an external CD exchanger, further differentiation is made between their respective instances via instance ID. Instance ID has a size of 8 bits. Its default value is 0x01. Fblock ID and instant ID together are called functional address of an Fblock. The combination of Fblock ID and instant ID must be unambiguous throughout the system. For its own Fblocks, a device itself is responsible for the suitable allocation of instant IDs. For example, by putting them into ascending numerical order starting with 0x01. The network master is responsible for functional addresses being unambiguous throughout the system. For example, two different physical devices implement a CD player and with the Fblock audio disc player, and each initializes the instant ID with 0x01. This means that the functional address 0x31.0x01 would exist twice in the most system. In the case of such a conflict, the network master must reset an instant ID as an alternative to dynamic handling of instant ID. They can be preset statically by the system integrator. The instant ID values 0x00 to 0xFF have a special function as wildcards. In case yes, device implements several Fblocks of a specific type, 0x00 addresses any instance of the corresponding Fblock on a given device. Don't care. 0xFF addresses all instances of the device broadcast. Well, wildcards can only be used in requests. The response messages must include the correct instant ID of the answering Fblock. For the case of systems Fblocks, the most specification requires a special handling of instant IDs for those blocks that must be implemented by every device, that is NetBlock and enhanced testability. The instant ID corresponds to the ring position starting with 0x00 for the timing master. It is increased by one of each device according to its position in the ring. The Fblock network master, where only one instance is allowed in the system, defaults to instant ID 0x01. The instant ID 0x00 is also allowed. In case of request, the wildcard 0x00 must be used. Functional identifier FKT ID. Individual functions of an Fblock are distinguished from one another through the FKT ID, which has a size of 12 bits. A function can either be a property, that is a variable of a Fblock, or a method. When a function is a property or a method, which operation it supports and which parameters are used. See the following section is defined by its interface description in the Fblock specification. The differentiation between properties and methods is discussed in detail in section 4.2.2, which also deals with the use of the respective function type and their usage. In the case of FKT IDs, the following subareas are differentiated. See table 4.3 functions from the coordination area of FKT ID 0x00 to 0x1 FF must be implemented by all most devices in the same manner. This area is coordinated by most cooperation via the general Fblock specification. Section 4.4.2, the application area FKT IDs 0x200 to 0x9FF defines functions that represent the main application for specific Fblock according to its Fblock specification. The unique area 0xA00 to 0xPFF contains functions which may only exists once in a most system. In this case, the system integrator has to take care to coordinate the usage throughout this whole system, similar to the Fblock IDs. The system integrator FKT IDs 0xC00 to 0xEFF or the device manufacturer FKT IDs 0F000 0xFFE can specify proprietary functions, name, FKT ID, area, description. Structure of the FKT ID, name, FKT ID, area, description, coordination, 0x00 to 0x1FF functions for administrative purpose in an Fblock that are coordinated by the most cooperation. Application 0x200 to 0x9FF function that represent the main application functionality of the Fblock. Unix 0A00 to 0BFF functions that are defined unambiguously in the entire system. System specific 0xC00 to 0xEFF function that can be used by an system integrator. Supplied as specific 0xF00 to 0xFFE function that can be used by a device manufacturer. Operation type, OPT type, depending on the type of function, property, or method, different basic operations can be applied to a function. Operations are the basic elements of the interaction patterns for properties and methods that are defined by the application protocol. An operation is specified by the OP type, which has a size of 4 bits. The following table shows the total of 16 individual operations. They have different meanings depending on the function of being a property or a method of the Fblock. The first 9 operations describe a request to the function and are thus used in messages that are sent by the controller to a slave. The last 7 operations describe the answers of the slave and are used in the corresponding reports. Operation types, OP types of properties, OP types of methods, OP type, request, set, start, deprecated 0x0, get, abort, deprecated 0x1, set, get, start, result, deprecated 0x2, increment, result 0x3, decrement, result 0x4, get interface 0x5, OPT method, start, result acknowledge 0x6, abort acknowledge 0x7, start acknowledge 0x8, response, error acknowledge 0x9, processing acknowledge 0xC, result, processing deprecated 0xP, status, result deprecated 0xC, result acknowledge 0xD, interface 0xE, error 0xF. The meaning of the different op types and their use in the operational sequence will be explained in section 4.2.2. The size of the data area length. The element length indicates the size of the data area in bytes and has a size of 16 bits. Therefore, a maximum of 65,535 bytes is possible with a length of 0, designating an empty data field. The length is not transmitted directly, but is calculated by the network service using the information of the underlying protocol, depending on the protocol, AMS or mosaic protocol. For example, when the AMS is used, since most specification 3.0, all op types for methods without a sender handle parameter are deprecated. The op types interface and get interface are optional. The op type error acknowledge may be written by a property if by mistake an acknowledgement of types has been used in a request. Op type error may be written by a method if the sender handle is not applicable or unknown. The length is calculated from the number of and the length of the individual telegrams on the control channel. Data and parameter types. If a function has one or more parameters, the corresponding parameter values are transmitted in the data field data. The types and sequence of the parameters are predetermined by the specification of the functions interface in the block specification. The most specification defines the parameter types indicated in the following table. Parameter types are most application protocol parameters, size, description, Boolean 1 byte, Boolean value, true or false, bit field 1, 2, 4, or 8 bytes, bit field with mask, enum 1 byte enumeration, unsigned byte 1 byte, integer value without sign, signed value 1 byte, signed integer value, unsigned word 2 bytes, integer value without sign, signed word 2 bytes, signed integer value, unsigned long 4 bytes, integer value without sign, signed long 4 bytes, signed integer value, string variable, null terminated string with encoding information, stream variables, a stream of arbitrary data, classified stream variable, a stream with type information, short stream up to variable up to 255 bytes, short stream with length information. The individual parameter types are summarized below. For a more detailed description, please see the MOS specification 3.0. The characteristics of the individual parameter types are similar to the parameters used in other programming languages. Boolean, a parameter type, Boolean can have one of the values true or false. Only the lowest value bit of the respective byte is used. Bit field, the parameter value type of the bit field specifies a bit sequence that can have a total size of 1, 2, 4, 8, or 8 as required. According to the MOS specification, the first of the parameter of the type bit field is a MOS, and the second of is its data. When the parameter performing an operation, the bits of the MOS indicate on which of the corresponding bits of the data the operation is to be applied. In practice, this parameter type is sometimes also used without a MOS. enum, a parameter of type enum, can adopt one of the maximum 256 possible predefined values. The individual values and their meanings are determined by the function's interface definition. Signed, unsigned byte, signed, unsigned word, signed, unsigned long integer values. The MOS specification supports the indicated integer values with a size of 1, 2, or 4 bytes, each with or without sign. For numerical values with sign, the sign is determined by the MOS significant bit, and the value is coded in 2's complement. The MOS specification up to version 3.0 does not provide specific parameter type of for floating point numbers. Instead, decimal place for the number parameters can be defined by indicating an exponent value in the interface definition. String, for transmission of character strings, the parameter type string is used. The first byte of the string indicates its coding, example 0x00 for the UTF-16 and 0x01 for ASCII. It is followed by null terminated character string in which 1, 2, or more bytes are used for each character depending on the coding. The end of the character string is characters by a null byte, 2 null bytes in the case of codings with 2 characters such as UTF-16. Stream, the parameter stream defines an arbitrary byte sequence and is used if no suitable description by the other parameter type is possible or if the dynamic data structure is required. If the parameter type stream is intended to be used together with other parameters, only one of the parameters may be stream, and it has to be a last parameter. Short stream, a short stream is intended for representing a short byte sequence. It has a maximum length of 256 characters, with the first character indicating the length of the subsequent byte sequence 255 byte at most. Because of the length information, it does not have the same restriction as the parameter stream and can be used anywhere in the sequence of a function's parameter. Classified stream, in the case of a classified stream, the first 2 bytes indicate the length of the stream and the subsequent null terminated ASCII string without coding information indicates a media type. The media type corresponds to one of the HTTP 1.1 specification or RFC 2616. To handle more flexible data structures, the concept of stream cases and stream signals has been introduced. Both are defined in the function's interface definition. With the stream cases and stream signals, a parameter of the type stream can be structured in 2 different ways. With stream cases, a parameter of type stream is further structured into different sequence of stream parameters depending on the value of a selector, similar to the concept of a variant recording in programming languages. The selector is a parameter of any type that has to occur before the stream. Often parameters of the type enum are used as selectors depending on the certain predefined values of the selector. The stream will consist of a sequence of stream parameters with different types and numbers. With the stream signals, a stream is divided into different consecutive named elements, each with an arbitrary number of bits. For detail on stream cases and stream signals, see MOS specification MOS 3.0. Dynamic behavior after describing the message format of the MOS specification protocol and its individual elements. This section deals with its use and the resulting message sequences. Querying the value of a property and with the operation get, controller slave, Fblock instant function get, alternate Fblock instant function status, data parameter value, Fblock instant function error, data error code, error info. Query and setting property, as already explained, a function is either a property or a method. A property describes a specific variable of an Fblock and consists of one or more parameter values. the values of all the parameters of an Fblock indicate its current status. The value of a property can be queried or set via the most specification protocol. In addition to that, the most specification specifies a notification mechanism by means of which a device which is interested in the value of the specific property is automatically informed of its changes. To query the current status of the property, a control message with the operation get of type 0x1 is sent to the corresponding function of the Fblock. If no error occurs, the later answers with a message containing the operation type status of type 0xc and the current value of the property in the data field. Otherwise, an error message of the operation type error 0xf is sent back. See the following section or error handling. Figure 4.3 shows the corresponding sequence as a message sequence chart. In MSC 2000 notation is at 0.12099 ITUT. This notation is used by the most cooperation, and we will also use it for describing the following examples. For a description of the MSC within the most specification, we have already done in Appendix A. Controller slave opt Fblock instant function set data parameter values written by Fblock instant function error data error code error info. The operation set of type 0x0 is used when no feedback is necessary after the value of a property is set. Only if an error occurs during the process, thus the Fblock answers with the corresponding error information. The operation set should be used when the controller has set a notation for the corresponding properties. See the following section concerning the notification mechanism. Setting the value of the property with the operation set get controller slave Fblock instant function set get data parameter values written by slaves sends Fblock instant function status data parameter values slave sends Fblock instant function error data error code error info. The set get operation of type 0x2 is similar to set, with the difference that a status message with the resulting new values of property is sent back as confirmation that the change was carried out. This way of accessing properties is to be preferred when a notification for a property is not used at the same time. Additionally, the most specification defines the operation increment of type 0x3 and decrement of type 0x4 by means of which the value of the property can be increased or decreased by an amount specified in the interface specification. These operations, however, are less commonly used compared to the other ones previously described. Also, they are more prone to errors as an unintentional retry increases or decreases the value by 2 steps instead of 1. Executing methods can be used to start a process that changes the status of the Fblock or representing a long-lasting process. Example, starting the station scan in this case of a radio receiver. A controller can start and, if necessary, abort methods. When starting the method, a sequence of parameters is optionally added which influences the behavior of the method, such as the direction of the station scan. The result, which are possibly generated by the method, in this case, for example, the list of stations, are then returned to the initiator. In order to differentiate between controllers within the device, example, different applications that are started a given method, all operations for the method additionally include a special parameter called center handle with the size of 16 bits. This parameter always returned by a called method together with the answer and enables the sender to associate the answer message with its command message. Since most specification 3.0, the corresponding operation types without sender handle and without the suffix acknowledgement are not used anymore. Starting a method with the operations start acknowledge, controller slave, Fblock instant function start acknowledge, data sender handle, parameter values, slave returns, Fblock instant function block error acknowledge, data sender error handle, error code, error info. Operation start acknowledge of type 0x8 is used to start a method for which a direct result is not expected or which triggers a continuous procedure. This corresponds to the operation set for the properties and also has the same op type. For a start acknowledge, the only feedback is in the form of an error message. If an error has occurred, method which generates a result and they report it back to the initiator are triggered by means of the operation start acknowledge. Op type 0x6, the initiator is informed of the result of the execution by means of the message with operation result acknowledge 0xd if no error has occurred during execution. If the calculation of the result takes longer, more than 100 millisecond, the initiator is informed every 100 millisecond of the ongoing calculation by means of a processing acknowledgement message 0x8, depending on the method. It is also possible that the intermediate results are transmitted within the processing message to indicate the progress of the function execution. The correct handling of processing messages and the appropriate error handling is important to guarantee the responsiveness of an application when implementing interactive HMIs. The timings described here are standard values as defined by the MOST specification. However, they can be defined differently for individual methods or by system integrator for the whole system. Starting a method with operation start acknowledge, controller save Fblock instant function start result acknowledge data center handle parameter value. Slave returns Fblock instant function processing acknowledge data center by handle intermediate value. Then slave return, it is in the loop. Then Fblock instant function result acknowledge data center handle result values, and Fblock instant function error acknowledge data center value error code error info are returned by the slave. By calling the operation abort acknowledge 0x7 on a running method, its current processing can be interpreted. This is signaled by an error message with the error code method aborted, by which is sent both to the initiator of the method and to the sender of the abort request in case the two are not the same. Notification mechanism. The MOST specification defines a notification mechanism so that a controller interested in a specific property does not have to constantly poll its current value using a get message. When defining a block, it is implicitly determined which properties support a notification mechanism or all of its properties supporting notifications. And Fblock administers a table called notification matrix in which the addresses of those devices are entered that have a set a notification for the respective property. As soon as the value of one of these properties changes, the Fblock sends a status message notification with the new value of the property to all devices listed in this table. A controller set or deletes a notification by calling its function notification FKTA ID 0x401 of the corresponding Fblock. The first parameter control indicates the operation. See the following listing in another parameter device ID. The address of the device requesting the notification is indicated. Finally, if required, the following list of FKTA IDs describe for which the function notification is requested. Set all requests a notification of indicated devices for all Fblocks properties for which a notification is supported. Set function requests a notification of the device for all Fblocks properties indicated in the subsequent list. Notification mechanism controller Fblock instant notification set data set functions device ID acknowledged by slave Fblock instant function status data parameter values. When value property has changed, slave returns Fblock instant function status data parameter values. Clear all deletes all notifications of the indicated device for all notified properties of the Fblock. Clear function deletes the notification of the device for the properties of the Fblock indicated in the subsequent list. If a notification of a property is set successfully, the Fblock sends a status message with the current value as confirmation, and an example for the use of the notification mechanism is given in section 4.4.4. Error codes of the MOST protocol, error name, error codes description, Fblock ID not available 0x01, syntax error, Fblock does not exist, instant ID not available 0x02, syntax error, instance does not exist, FKT ID not available 0x03, syntax error, function does not exist, OPT type not available 0x04, syntax error, operation is not defined, length, invalid length 0x, length of data field is not identical with the interface specification, parameter wrong out of range 0x06, wrong, one or more parameters were wrong, that is not within the boundaries of the specified function. Parameter value not available 0x07, one or more of the parameters were within the boundaries specified by the function but not available at that time. Reserve 0x08 is duplicated, reserve 0x09 use is duplicated, reserve 0x0a use is duplicated, device malfunction 0x0b, device general device error, segmentation error 0x0c, error during desegmentation messages by the AMS, function specific 0x20, function specific error BC 0x40, function is available but is currently being executed, not available 0x41, function is implemented in principle but is not available at the moment, processing as 0x42, general error during execution of a method. Method aborted 0x43. This error code is used to indicate that a method has been aborted by the abort acknowledge operation. System specific 0xC0 or 0x20xCEF error codes that are defined by the system integrator. Supplier specific 0xF0 to 0xFE error codes that are defined by a device manufacturer. Error information: if an error occurs during the execution of a request, whether a property or a method, a message of the operation type error or error acknowledge or OP type 0F or OP type 0x9 is written, the error code, parameter error code is transmitted in the first byte of a data field. The second byte contains the parameter error info with additional information depending on the error code, which will not be discussed here. For more detailed description, see the most specification, most 3.0. There are some specific requirements concerning error responses in most system. In order to avoid a cyclical sending of the error information, error messages may only be sent from the slave to the controller, with the exception of the segmentation error. The general error information shown in table 4.6 is specified by the most specification. Most function blocks. This section goes into details of the structure of an F block and describe the most important aspects that have been to be observed for its definition. Besides the general structure of an F block, the concept of function classes is described, which provides guidelines for defining the individual functions of an F block. Additionally, the system F blocks, such as net block required for administrative tasks in the most system, are introduced in this section. Finally, the functions are described that are required for the administration of streaming connections and for the transmission of multimedia data. Structure of a function block. The function block, F block specification defines which function belongs to an F block of a specific type. The type of an F block is determined by F block ID. The most cooperation standardizes a set of F block types, some of which are used for system tasks. Other describes a certain application functionality. The latter are then often extended by device manufacturers and system integrators to integrate their own proprietary functions. Other F block specifications are defined completely by the system integrator or defined manufacturer, either because they define a proprietary functionality or a new functionality for which a standardized F block specification does not yet exist. The F block standardized by most cooperation are collected in a function library. For all F blocks, the following functions are not required by the most specification. FKTID 0x00, a list of all functions implemented by the F block, can be queried by the property FKTID. In order to compress this possibility long list of FKTIDs, a coding is used in which only those FKTIDs are included in the list in which there is a transition between a continuous area of implemented and non-implemented functions. F block info, FKTID 0x011, this mandatory function returns information about the F block's name and version, the version of the most specification. The F block has been implemented for the system integrated in whose system the F block will be used, and a string F block type that is assigned to by the system integrator to identify different instances of the same F block in the system. Example, a left and a right displayed unit for a rear seat entertainment system. Notification FKTID 0x401, the property notification must be implemented by every F block that allows setting of notification for one or more of its property. By means of this property, a device can set or delete notifications. Notification check FKTID 0x402, the optional property notification check can be used to check which notifications are currently set. In addition to these functions, each F block must implement the functions from the coordinated range that are indicated as conditional according to the respective precondition defined in the general F block specification Gen FB. Furthermore, all functions defined as mandatory in the corresponding F block specification have to be implemented. Functions that are indicated as optional may be omitted. When defining and deploying a MOS system, the system integrator indicates in detail the devices that make up the system and the F blocks which are to be implemented by each device. Usually, the system integrator also indicates in detail which functions are to be implemented by the individual blocks. Function classes simplify the specification of a block by giving specific guidelines concerning the data types and the operation of a function. A function class is assigned to a function in a block specification and specifies particular settings for the parameters of a function, such as the maximum length of a sequence of characters. Additionally, a function class defines which operations can be executed on the corresponding function. Finally, function classes are the basis for complex compound type data types such as records or arrays. Function classes enable a structured and uniform modeling of functions. Additionally, they support the use of tools for modeling and code generation and simply test automation. If a function cannot be assigned to any of the function classes described below, it is assigned to the function called class unclassified property for properties and unclassified methods for methods. The most specifications specifies the following simple function classes for properties, the status of which can be described with a single parameter. A switch, the function class switch encapsulates the Boolean parameter and describe a switch with two states which can be set and read. Number, the function class number is used for different parameter types of signed and unsigned numerical values. This function class has the following setting: the parameter type, its maximum and minimum value, and exponent defining the decimal place, and the increment by which the numerical value is changed by increment and decrement operation. Text, the function class text is based on parameter type string and defines a sequence of characters. Its setting indicates the maximum length of the string. Enumeration type are described by the function class enumeration and are based on an unsigned byte. This function class defines how many elements the enumeration type has and what values they can have, including an textual description. For example, the function text status of the Fblock auction can have the value 0x00 for play, 0x01 for stop, 0x02 for pause, etc. Boolean bool field, the function class bool field defines a sequence of bits with a length of 86 for the 32 bits in total and is based on unsigned byte, word or long respectively. It is also permitted to structure the bit sequence into addressable elements of several consecutive bits, leading bits which are not used remain empty. Bit set, a property whose status can be described by a parameter type bit field, is assigned to the function class bit set with a given length as defined for parameter type bit field. Its first of contains the mask and its second of the data. Container, finally, the function class container is used for further unstructured data. This function class is based on a parameter type stream, classified stream or short stream. Its setting defines the maximum allowed length. Additional functional classes are used to represent more complex data structures consisting of several parameters. For these function classes, a leading parameter position is used to indicate the individual elements which are to be assessed. Position consists of the two parts, parsecs, parse y of 1 byte. Each parsecs indicates a position in the outer data structure, parse y the position in a possible inner data structure. In the case of a two-dimensional array, parsecs indicate a certain row and parsecs, parse y and column. If parsecs is not equal to 0 or parse y is 0, the entire row of the array is used. With parsecs and parse y 0, the array is addressed as a one. For properties, there are the following structured function classes. Record. A record consists of an arbitrary sequence of individual elements, each with a certain function class where individual elements can be accessed by the parameter parsecs. Structured function classes such as an array are all allowed as elements. In this case, parse array is used to address the elements of the array. An array describes a sequence of maximum 2 to 6 elements of the same type, which can also be accessed individually by the parameter parsecs. The setting of the function called class array indicate the function class of the individual elements and the maximum length of the array. Dynamic array. The dynamic array is a variant of an array in which the individual elements are accessed via 16-bit tag instead of parsecs. In this case, longer arrays are possible. Additionally, functions for inserting and deleting elements are defined. Since the tag of an element, unlike its position, does not change when it is inserted or deleted, the dynamic array is also well suited for more dynamic data structures. long array, in the case of a long array, the individual elements are also accessed via a 16-bit tag. Additionally, a window mechanism is defined by means of which a controller defines a specific section window array of the array. Afterwards, it is informed only about changes in this section, which enables an efficient HMI implementation for displaying a list of where only the current visible section according to the screen size is updated. Example for displaying the phone book of a cell phone. Map, the function class map is similar to the dynamic array. However, in addition to it is able to transmit the insertion or deletion of a single or multiple lines by a notification. Therefore, updates for a function of class map can be transmitted very efficiently. Sequence properties, the functions called sequence property is a simple function class by means of which a sequence individual elements can be set and read. Multidimensional data types and separate access to individual elements are not supported. For methods, only the following two functions classes are defined besides unclassified methods. Trigger, function class trigger describes a function class without parameters, which triggers a specification. Sequence method, the function class sequence method is a function class for methods which a list of simple parameters. Function interfaces, since most specification 3.0, the mechanism of function interfaces is optional. Usually, the concept of function classes is only necessary for definition of a function. Retrieving information about the function interface, that is function class and its settings during runtime is not common. The most specification specifies the optional operation get interface of type 0x5 to request functions, function interface. The result transmitted is via the operation interface, OPT type 0xC. Coding of the relevant information is detailed in most specification. System Fblocks. This section gives an overview of Fblocks which are required by the most specification for the purpose of system administration. As mentioned earlier, there are Fblocks implemented in all devices of a most system, and Fblocks are only provided for one specific device. NetBlock, Fblock 0x01. NetBlock is responsible for central tasks of the system administration concerning a certain most device. It must be implemented by every device in a most system. The most important functions of the NetBlock are described below. The complete interface of NetBlock is specified in NetBlock. Fblock ID, FKT ID 0x00, the function Fblock ID returns a list of all active application Fblocks that are offered by the device as pairs of Fblock ID and instant ID. Since Fblock, like the NetBlock itself or the Fblock enhanced testability are not included, and Fblock may only be included in this function if it is correctly initialized and currently able to offer its functionality to a controller in the most system. Furthermore, the function Fblock's ID can be used to set the instant ID of an Fblock. Its main use is during the system scan of the NetBlock work master. Device info, FKT ID 0x001, queries characteristics parameters of the device, such as the name of the manufacturer, the serial number, addressing functions. Further functions provide information about the node position address. Node position address FKT ID 0x002, the logical address node address FKT ID 0x003, the group address FKT ID 004 of the device. Shutdown FKT ID 00x06, and the shutdown procedure of remote system is controlled through this function. Shutdown reason FKT ID 0x009, after a startup of remote system, a unique controller may query the reason for the shutdown from each device. In case of a shutdown, because of a failure, sudden signal of or critical unlock, each device that has detected such failure returns suspected information through this function. Implementation Fblock ID, FKT ID 0x012. This optional function returns the list of Fblocks of all Fblocks implemented by the device. In contrast to the functions Fblocks, also the Fblocks that are not currently available can be queried. RBD request Fblock ID FKT ID 0x4005. 405. The result of a ring break diagnosis is transmitted within this function. For details, see chapter 8. Boundary FKT ID 0803. This function is only available on a device which acts as the timing master. It enables administration of bandwidth allocation on the data link layer, read out and set. The corresponding mechanism described in section 5.1. Fblock enhanced testability, Fblock 0x0F. The Fblock enhanced testability ET is necessary to perform the tests required for the core compliance of the most device, core 3.0, and most must be implemented by each device. These tests check basic system functions of the device, such as the allocation of an address. The details of the functions of the Fblock ET will not be given in this context. It is described in detail in the FBET. The block ET offers functions for test automation. The function reset FKTID 0x21, for example, can be used to reset the device in order to start from a stable state. It also contains functions for executing a functionality which can otherwise not be triggered automatically, such as the function auto wake up FKTID 0x201, which simulates simultaneous wake up of the device. Fblock network master, Fblock ID 0x02. The Fblock network master is responsible for the central administration of the system configuration of the MOS system. It is thus mandatory for each MOS system and must be implemented by the designated device. Often a specific device is responsible for the master, all master functionalities in the MOS system, which means that the device is usually not only network master, but also timing master, connection master, and power master. However, except for the network master and timing master, this is not mandatory. The network administers the system configuration, and thus the current system status, the MOS system, the system state is okay. If the current system configuration, that is the devices existing in the system and that blocks are known to the network block or master, otherwise the system is not okay. The system is in not okay state directly after startup, or if an invalid configuration has occurred after network change event due to an invalid device address. In order to determine the system configuration during a startup or after a network change event, the network monitor executes a system scan in which it queries the Fblock of all devices via function Fblock IDs. This query is sent with the physical device address. If there is a valid configuration and the system status was not okay, the system state changes to okay, and the network master notifies the device in the MOS system by means of a broadcast of the function configuration. The parameter configuration control indicates the system state, in this case okay. Figure 4.99 shows the operational sequence of a system scan. In practice, Fblocks also can be queried in parallel. After the initial system scan, device may also inform the network master of new or disabled Fblocks by sending a status message of the function Fblock IDs with a new list of Fblocks in the system state. It was okay before a system scan, or the network master is informed of a change in the Fblocks offered by the device. The network master describes the information about any added or disabled Fblocks to the MOS system via the function configuration. In the first case, the parameter configuration has the value new exe. In the second case, it has a value invalid with the additional parameter delta Fblockless ls with block IDs, instant IDs, and in case of new exe, the logical address of the respective Fblocks is included. If during a system scan, a conflict occurs between the function addresses of the Fblocks, which means that several instances of an Fblock have the same instant ID, the network master tries to resolve the conflict by resetting the instant ID that was reported lost. If an error occurs, such an invalid address which cannot be solved by resetting instant ID, the network master sets the system state to not okay, and thus triggers a new startup of the system. The information on the current configuration of the MOS system is stored by the network master in a central database, the central registry. The central registry stores the logical address of each device in the system, as well as a list of implemented blocks with their instant IDs. And the other devices in the system can query its current configuration via the function central registry, and thus determines the device address associated with the functional address of a communication partner. If the higher level of network services are used, this mechanism is executed automatically. An operational sequence of a system scan network master is shown here. The Fblock network master implements the following functions: the configuration FKTID A00 with the function configuration. The network master disseminates information about the system state in a MOS system by means of the broadcast. The parameter configuration control as the values okay or not okay. Additionally, newly added or disabled Fblocks are announced. Configuration control, new EXT are invalid. Central registry FKTID 001 enables the querying current central registry. The complete central registry can be queried. All instances of a given Fblock can be retrieved, or a specific instance of an Fblock is queried. The function central registry returns corresponding list of Uplatz of logical devices addresses Fblock ID and instant ID. System available FKTID 0xA10. Corresponding optional mechanism provides information about the availability of the system. To this end, the network master queries the function implement Fblock ID of all devices in the system with the parameters device avail and Fblock avail. A slave device may determine if all devices have correctly responded to the network master and if any all implemented Fblocks are currently available. Fblock connection master, Fblock ID 0x03. The Fblock connection master is used for administration of the streaming connections in the mouse system. It will be discussed in the next section. Fblock power master, Fblock ID 0x04. There is no particular Fblock specified for power master. The Fblock ID 0x04 is only used for indicating the device with the corresponding functionality. The power master is responsible for coordinating the shutdown of most systems. This may be a regular shutdown, for example, when the engine is switched off, or an emergency measure, for example, when the temperature is too high. To shut down the other devices in the most system, the power master uses the function shutdown of the net block. It announces the shutdown by sending a shutdown, start acknowledge, center, handle, or query message as a broadcast. This enables the other devices to delay the shutdown by means of a shutdown, result acknowledge, center handle, suspend message. Depending on the system architecture, an ongoing telephone call, for example, could prevent the shutdown. The power master repeats the announcement of the shutdown at regular intervals. If it does not return a shutdown, result acknowledge, center handle, suspend message as a response. It initiates the actual procedure for shutdown by broadcasting the message shutdown start acknowledge, center handle execute. If the device detects a high temperature, it can force the shutdown of the system by broadcasting the shutdown, result acknowledge, center handle, temperature shutdown message. The power master then executes the above described procedure for a normal shutdown of the system. Administrative of streaming connection, due to the fact that the transmission of a multimedia data is a central application or area of the most system, the administration of the streaming connections, which are not used to transmit audio or video data, play a central role in most systems. The following section deals with the mechanisms and interfaces provided for the application layer.